Namaskar friends, welcome to session 39 of our course on manufacturing guidelines for product design. So currently we are in the last week of our discussion and we started this week with a very important concept of design for environment. Now we are trying to finally achieve that target of prototyping the product. Initially we have seen that what are the guidelines that we must keep in mind when we are designing the product, which has to be manufactured using any of the standard manufacturing processes. In the course of our discussion, we have discussed the design guidelines for products which are going to be made by casting process, guidelines for products to be made by die casting process, guidelines for the various manufacturing processes for plastics such as injection molding, compression molding. Then we have seen that once the product has been formed, if it has to be joined together, what are the guidelines? We have seen different types of joining processes, and if you remember in the last 2 weeks of our discussion, that is week number 6 and week number 7, our target was to learn about the various joining strategies that can be used for assembly of the product, or for we can say adhesive joining or welding or brazing or soldering or vibration welding or ultrasonic welding or microwave welding or hole making. So all that was the target of our discussion in week number 6 and week number 7. So in overall summary, what we have learnt is that once we are designing a product, and we have to decide that which process we are going to adopt to manufacture this product. Now different processes are there, and the very first week focused on the overview of the manufacturing processes. The second week our focus was on the engineering materials. So once we have finalized our design, we have to finalize the material which is going to be used for making the product, as well as we have to finalize the manufacturing process which is going to be used for manufacturing of the product. So once the materials are finalized, the processes are finalized, we have to then think that how easily we can manufacture the product. And for that, all the guidelines that we have discussed in this course are going to help the designers. I must address that today we are at the fag end of our course. Today is the 39th session that we are discussing this topic of rapid prototyping, but there is a lot of information which is available. We have been only able to touch the tip of the iceberg only. There is a lot of additional information which is available. There are different books which give additional guidelines related to various processes. For example, we have taken design for machining, only 25 minutes of discussion, 5 minutes of revision, 25 minutes of discussion. There are chapters which have been written on the design for machining guidelines, that if the product has to be machined or the parts of the products have to be machined or have to be processed using the machining processes, what are the various types of guidelines that must be kept in mind. Similarly, when the product has to be joined together using the welding process, what are the various types of guidelines that must be kept in mind. Although we had discussion on joint designs which are going to be used for welding processes and what are the joint design modifications that can be done, all that we have discussed, but I must address that there are a lot of other information also available which we must look into when we are designing our product. So that is an important thing that I feel that when we are closing the course now, lecture number 39 is today, maybe we will be finalizing with our last session, that is session number 40, where we will try to sum up what we have already covered and establish a sequence of steps that we must follow when we are doing the analysis of our design from the manufacturing point of view, because we analyze the design from various perspectives. So our target during this course was to analyze the design, to modify the design, to redesign the part, keeping in mind the manufacturing guidelines, so that our product that we are planning is easy to manufacture. So all those guidelines basically we have tried to cover. Only the summary of the guidelines, again I am reiterating, there are other guidelines also. So once the product has been designed, all guidelines have been taken care of. Now we are confident that the manufacturing guidelines for the product design have been taken care of. We will go to the next stage, that is the prototyping. Once our design is ready, we know the material that is going to be used, we know the process or the type of processes or the sequence of processes that are to be followed to finalize the design or to manufacture the product. We will next go to the stage of prototyping. In prototyping, we are these days focusing on rapid prototyping. Maybe 25 years, 30 years, 40 years back, maybe in the 1960s or 70s, we were using very traditional methods of prototyping, but today we have a technology called rapid prototyping, in which very quickly, in the shortest possible time duration, we try to make our prototype. Because of the information technology, because of the development of computing machines, because of the development of computer aided design, we are easily able to convert our design from the system, from the computer, into a three-dimensional model using various strategies and technologies. Now, rapid prototyping, long time back I have read that there are 70 to 80 different technologies that fall under rapid prototyping domain, but we may not be able to cover all these strategies. We have already covered 3 to 4 processes when we completed our course on product design and development, which has been successfully run twice under the MOOCs platform. So, in that case we have discussed what is rapid prototyping and what are the various processes that fall under rapid prototyping, and then we try to understand the mechanism of working of 2 or 3 processes. But here our target is not that what is rapid prototyping and what are the types of processes that fall under rapid prototyping. Our target is that once we are prototyping our part, what are the things that we must keep in mind while finalizing our rapid prototyping process. So, with that background, we will try to cover the today's session, that what are the guidelines that we must keep in mind once we are going to rapid prototype our product, or we are going to 3D print our product, or we are trying to make our prototype using the fused deposition modeling, or we are going to make our prototype using the selective laser sintering, or we are going to adopt the process of stereolithography apparatus. So, there are number of processes, but there are few general guidelines that we must keep in mind once we are doing the rapid prototyping of our design, which we have already finalized. We have taken care of all the manufacturing guidelines. If there are holes to be produced in the product, we have taken care of that the adequate center to center distance must be there between the hole. We have taken care that the center of the hole is adequately at a distance from the edge of the plate. So, all those guidelines we have taken care. Now, we are going to the next stage. We are going to make a prototype, a model of our product, and see that whether the product as we have designed it is looking like that, or there are some interference problem when we are trying to join the two parts together, or they are not fitting into each other. So, all those things can be checked during the rapid prototyping stage. So, rapid prototyping is a crucial step in any product development cycle, and we cannot ignore the importance of rapid prototyping, or I must say prototyping. So, let us quickly go through the basic steps that we follow in rapid prototyping, and then we will try to go to the guidelines that we have to follow when we are going to prototype our product using any of the standard approaches of rapid prototyping. And one thing I must address here, there is a good article which was presented by Zaragova and Hugo on design for rapid prototyping, manufacturing and tooling guidelines. So, some of the data that we are presenting here in today's session is taken from this very good article which has been published, and they have tried to, the authors have tried to compile the information and produce a standard document which can be used by people worldwide who are using rapid prototyping processes. But many things, maybe with the advent of new processes coming into picture, some of the things may need certain revision, but these serve as a good guideline for the people or for the engineers who are working in the area of rapid prototyping. So let us quickly see what is rapid prototyping, just maybe very briefly. Now, rapid prototyping techniques are being developed as an alternative to subtractive processes. Now, what are the subtractive processes? All of you may be knowing the subtractive processes are the normally the machining processes where we try to remove the material from the workpiece and try to create a model. So, rapid prototyping processes are usually additive fabrication processes. Many times we say additive manufacturing also. We try to produce our prototype layer by layer instead of taking a bigger piece of the raw material and then cutting the additional parts of the material to create a shape. Here we try to create the shape layer by layer, thus eliminating the wastage of material. That is usually we can say limitation in case of subtractive processes. So, rapid prototyping techniques are being developed as an alternative to the subtractive processes. These systems are also known by the names of additive fabrication, as I have already told, additive manufacturing, 3-dimensional printing, very common rapid prototyping technique, 3D printing, then solid free form fabrication, layered manufacturing. There is a process called laminated object manufacturing, which is LOM, laminated object manufacturing. So, different strategies, different processes are there that fall under the broad umbrella of rapid prototyping. Now, they can be classified based on the type of raw material that is being used in a process where we can use a photosensitive liquid polymer, we can call it a stereolithography apparatus, where photosensitive polymer is used as the raw material. In case of selective laser sintering, we use powder as the raw material. In case of laminated object manufacturing, we use sheets as the raw material. So, we can classify the rapid prototyping processes based on a number of factors. One of the factors can be the type of raw material that we are using. Now, rapid prototyping technologies are able to produce physical model. So, this is very important, physical model in a layer by layer. This is very important and already highlighted. We make a prototype layer by layer, a layer on top of the other layer directly from their CAD models. As I have already highlighted, with the development in our computational systems, CAD models are being developed for most of the 3-dimensional objects, and then these models can easily be used to create a prototype layer by layer, one layer on top of the other without any tools. Now, this is another advantage. Without any tools, dies, fixtures, and are also with little human intervention. Very important advantages of rapid prototyping. First thing can be from the name itself, rapid and prototyping, which means we are saving time. Quickly we are able to convert our ideas into the prototype. We just have to create a CAD model of our idea, and then using any of the interface between the CAD model and the rapid prototyping strategy. Number of strategies I have already named, such as fused deposition modeling, selective laser sintering, stereolithography apparatus. So, different strategies are there. Using any of the strategies, this CAD model can be easily converted into a physical prototype of the product. So, that is one advantage is already there, that rapid means it is time saving. Additional advantages are no need of tools, dies or fixtures, because the product is made layer by layer by layer by layer, and the process is majorly automated. So, automatic process is used, so the human intervention is also minimized. So, rapid prototyping is capable to fabricate parts quickly. I need not explain it again, already I have highlighted the point. With complex shapes, another advantage of rapid prototyping, that very complex shapes which are otherwise not possible with the conventional processes. If you remember, we have seen in most of the conventional processes, shape complexity is a major limitation. So, here the shape complexity is not at all a limitation. We can create very complicated shapes using the rapid prototyping processes. So, complex shapes easily can be made as computer traditional manufacturing technology. Rapid prototyping helps in earlier detection and reduction of the design errors. As I have highlighted in the beginning of today's session only, that if 3 or 4 parts have to be joined together, we can create these parts from their CAD models easily using any of the rapid prototyping processes, and then we can try to assemble them and try to see the kind of interference, whether they are looking good or not, or what kind of joint can be better designed. So if there is a faulty design of a joint, it can be improved. So early detection of errors and remedial measures can be taken accordingly. So this will reduce the design errors. Now rapid prototyping we are doing after our design has already been finalized. So design is ready, now we are trying to prototype it. During the design we have taken care of all the guidelines that we have discussed till today. So these guidelines we are now trying to check using prototyping, and if there is a problem we will go back and try to change our design based on the various manufacturing guidelines that are known to us. So therefore rapid prototyping is giving us, or is increasing the timely manner in which we are able to launch our product in the market, or are helping us to manage our time more effectively and efficiently, because quickly we are able to detect the error, immediately we take a remedial action, again we prototype and see whether the product is ready, or product is ready to be manufactured or not. So we save time using the rapid prototyping strategies. Now what is the methodology? A very common diagram which is given in most of the books. So the rapid prototyping in its basic form can be described as the production of 3-dimensional physical parts from computer aided design data in the decreased time scale. So time is less, CAD model is required. We have a rapid prototyping system which will create the CAD model into a physical object, or 3-dimensional CAD model into a physical object. So we can see here step by step. First step is a CAD model of the part. So you have a product, you make the CAD model on your computer system, tessellation is done, maybe triangulation, then slicing. Because we make the product layer by layer, we have to decide how many layers the product will be made up of. Then we try to use, this is a rapid prototyping system, it can be any system, it can be SLA, it can be selective laser sintering, it can be laminated object manufacturing, it can be 3D printing system. So we can choose any of the strategy, and then the prototype will be ready. We will do the post processing or curing of the prototype, and finally it will be ready for the testing. So this is a standard approach. We need a CAD model, then we have to do the pre-processing in which we decide the number of layers, the thickness of individual layer, and then we take this file into our rapid prototyping system, where the physical 3-dimensional object is created or the prototype is created. Then we do the post processing, some additional maybe support material if we have used during the creation of our 3D prototype, that has to be removed. Sometime additional curing may be required, sometime some surface treatment may be required, surface cleaning may be required. So all that is done during the post processing of the prototypes, and finally our prototype is ready to be used or to be checked. So for this process there are standard guidelines that have to be taken into account. Now what are the design guidelines which are there? Let us try to see those guidelines. First thing is how big prototype we can produce. So the average workspace, so I must say the word average here is very important, because as I have already told that 70 to 80 different processes fall under the broad umbrella of rapid prototyping. So the average workspace available in commercial RP system is, so this is general, it is not specific to any one rapid prototyping strategy or process. It is a general guideline that we can have 150 millimeter to 380 millimeter in X direction, 150 to 390 in Y, and 150 to 380 in Z direction. So there are 3 directions, maybe X, Y and Z. So in all the directions the dimensions are given, that what can be the maximum size of the prototype that we can produce. Parts designed for RP must consider this workspace size. So maybe different types of machines will have different types of workspace arrangement or the size of the biggest size of prototype that you can produce. So all those things have to be taken into account when you are designing your product. Many a times it may so happen that our product is much larger in size as compared to the workspace available in the rapid prototyping machine. So what we can do, we can scale down our model also, so that the prototype that we are creating is a scaled down prototype as per the dimensions available in the machine that we are using for creating a physical 3-dimensional object. So all those possibilities do exist, and we must take care or take advantage of these possibilities wherever possible. So regarding the part size, when a part is too large, decompose it into smaller sections. So that can also be done. Suppose we want to create a model of a very large size torch, which is not possible to be created in a single part. So what we can do, we can decompose the complete product into, or we can explode the product into individual parts, and each part can be created using any of the rapid prototyping machines, and then we can assemble the parts. So when a part is too large, important guideline, decompose it into smaller sections, avoiding the appearance of, so we must decompose or divide it into smaller sections, taking care of sharp edges, thin walls. So thin walls must not be there, otherwise maybe there may be deformation or deflection taking place, small features, overhangs and enclosed cavity in the resultant sections. So we must decompose the bigger product into smaller products, taking into account, we must into smaller section, avoiding, we must avoid, what we must avoid, sharp edges, thin walls, small features, overhangs and enclosed cavities in the resultant sections. So we can decompose the large part into smaller parts, but all these guidelines we must keep in mind, otherwise even the smaller parts will become difficult to fabricate using the rapid prototyping processes. The use of incorrect layer thickness can cause breakable walls and geometry deformations. So layer thickness, as I have already told, suppose we want to make a product like this, a triangular section. So we have to decide that in how many layers this material will be made using the rapid prototyping process. So suppose this is the platen, so this will be made on this platen, and this is the RP part that we want to produce. Now we want to decide this individual layer thickness, suppose x, how much be this layer thickness. So the use of the incorrect layer thickness can cause breakable walls and geometrical deformations. The values of layer thickness to produce specific wall thicknesses are, now how much be the layer thickness to produce a specific wall thickness, that because every product will have some wall thickness. For example, in order to make it easy to understand, let us take example of a mineral water bottle or a plastic bottle that we use, or a cold drink bottle that we use, a plastic bottle. So it has got a wall thickness. So that wall thickness is important, and the thickness of the individual layers that are getting deposited is in a ratio of the wall thickness of the product. So that wall thickness has to be ensured with the help of these individual layers that we are depositing in rapid prototyping. So we can see this table gives us a very good idea that the layer thickness, suppose 0.007 inch. So the minimum wall thickness that we must get is 0.028 inches, or in millimeter if we talk about it is 0.18 millimeter layer thickness, minimum wall thickness is 0.71 millimeter. So the values of layer thickness to produce specific wall thickness are, so these are the minimum wall thickness for dispensing process. So layer thickness is in relation to the wall thickness of the product that we are going to produce. So this table must be taken into account. So depending upon the layer thickness, we can have our minimum wall thickness. But what I will say is that when we are designing our product, we are not bothered about the layer thickness at that point. We design the product, the various wall thicknesses we decide in our product. So, once the wall thickness is known to me, I can see that what must be the layer thickness that we must use. So, based on the wall thickness that is finalized in my product design, I can get a guideline that what must be my layer thickness when I am depositing the material to produce the product. Now, for dispensing process, maybe one category of the rapid prototyping processes, such as example is given fused deposition modeling. Wall thicknesses I have already told must be at least 4 times greater than the layer thickness. So, whatever layer thickness we have decided, and if you go back to the previous slide, we can see it is already there. 0.8 millimeter multiplied by 4, you will somewhere get 0.72 millimeter. So, 4 times the wall thickness. So, layer thickness must be 1/4 of the minimum wall thickness, or in the next slide we have written that minimum wall thickness must be 4 times the layer thickness. So, layer thickness is your 0.18. So, maybe we multiply it by 4, we will get 0.72. So, that is, we can say that 4 times of the layer thickness we will get the minimum wall thickness. For sintering process, the recommended minimum wall thickness is 1 millimeter, and for SLA the recommended minimum wall thickness is 0.508 millimeter. So, these are the other two processes, sintering process and this is stereolithography apparatus. The minimum wall thickness is given. So, once we are trying to make a prototype using these two processes, the minimum wall thickness is already specified, and this wall thickness is not a new term that we are using in today's session. We have used this term in case of injection molding process also, we have used this term in case of sand casting process also, we have used this term in case of die casting process also. So, for rapid prototyping processes also the minimum wall thickness has been specified. So, when we are designing our part and we know that this part has to be made by the prototyping process, maybe SLA, we must take care of the wall thickness requirements. So, for sintering process the recommended wall thickness is 1 millimeter, and for SLA the recommended wall thickness is 0.508 millimeter. A post processing is required to obtain the closed tolerances in the hole. So, this is another guideline. As I have already told, once our physical prototype is ready, we have to do the post processing in order to get a final finished prototype. Holes should be oriented in such a way that their axes are perpendicular to the building platform. So, as I have already drawn one picture in the previous slide. So, suppose this is a building platform and this is the prototype that we are trying to produce. So, what must be the orientation of the hole or the axis of the hole? The hole should be oriented in such a way that their axes are perpendicular to the building platform. So, this is our building platform, and we have to see that what must be the axis of the hole. So, we will like to have the hole like this. This is the center axis. So, the axis of the hole must be perpendicular to the building platform. So, this is the perpendicularity which is shown here. So, these are the specific guidelines that we must take care of. Now, if there are fillets and knife edges, if required, square corners should be rounded. So, we must avoid the use of square corners and we must try to round them off. Sharp edges should not be less than 0.8 millimeter for sintering processes. So, sharp edges must be avoided. It is range is also given, should not be less than 0.8 millimeter. Do not locate small features in areas that require support structures. Now, in many cases I must address this support structure issue here, that once we are trying to create a 3D model using any of the rapid prototyping processes, usually two types of material is used. One is the build material, another one is the support material. So the build material will actually create the prototype, and the support material will support wherever some overhanging portions are there, or wherever some sectional thicknesses are such that there is a tendency of this material or the build material to deform. So therefore in those cases we will reinforce it with the supporting structures or the supporting materials. So this is an important guideline here, that do not locate small features in areas that require the support structure. So these small features can be maybe deformed during the process, so we must avoid these small features near the support structures, otherwise they may get damaged during the removal of such structure. So when you are at the end of your rapid prototyping process, we will go for the post processing, wherein we will be removing all these support structures. So if we have a very small feature near to the support structure and we are trying to remove the support structure, this small feature may also get damaged. So that must be taken into account when we are maybe trying to rapid prototype a part. Geometrical features can be produced in RP systems as long as they are within the capabilities of the equipment and process. This is a summary of what we have discussed here. So whatever is the capability of the process, we can make the parts as per the process capability. Now part orientation is also very important. The part should be oriented with the minimum height matching the build orientation perpendicular to the construction platform. So again, suppose this is the construction platform which is going to move up and down. So we have to, the part should be oriented with the minimum height matching the build orientation. So minimum height we have to see what is the minimum height, and it must match with the build orientation. The amount of support structure should be minimized. This is very important, that we must try to minimize the support structures that are going to be used for making our prototype. The largest surface of the model should be supported on the building platform, especially in the dispensing processes. Now suppose our product is, let us take another example. This is a platen, this is our platen which will move, maybe suppose it moves down. So the product is, suppose, something like this. So the largest surface must be there on the platen. So that is the guideline. This guideline states that the largest surface of the model should be supported on the building platform, especially in the dispensing processes. One of the examples of dispensing process is the fused deposition modeling. An adaptive layer thickness should be employed to minimize the building time. So that is another maybe approach in most of the rapid prototyping systems, that is adaptive layer thickness system must be used to employed. So in next slide we will see that what is the difference between adaptive type of layer thickness system and a general layer system. So layer orientation and path planning. Visual models should be filled using an open array in order to reduce the material usage and cost. So visual models should be filled using an open array in order to reduce the material usage and cost. Now there are open array, we can select the fill density in our model as per our choice. So maybe in many cases we just want to see that how the product will look like. So we need not make a very dense rapid prototyped product, because if we make it very dense, maybe suppose we select in one of the rapid prototyping systems 100% density. So 100% density means that it will be fully dense product. We just want to see the shape. So there is no need of making it 100% dense. We can make it, we can select 50% density also, we can select 30% density also. So the visual models should be filled using an open array in order to reduce the, so for suppose we set 50% density or 30% density, different machines will have different levels, but if we select a less denser product, we will save the material, reduce the material usage, as well as the cost will be less. Parts that will be under mechanical stress. Now suppose we have developed a fully functional prototype, so the part is under mechanical stress, so we are going to test it for some specific requirement. So parts that will be under mechanical stress, a closed and alternating filling pattern should be used to increase the mechanical strength and reduce the orthotropy effect. So what we need to do here, that we must use a alternating filling pattern. Alternating filling pattern means that suppose this is my head or the gun which is depositing the material, I must deposit the material in a alternating pattern. So that is an important guideline that we must take into account. We have seen that how much dense part we must make, what must be our deposition pattern or the filling pattern, because that will decide that how much load the prototype can take. So that is also an important guideline, that we must have a alternating filling pattern in order to make it a good strength part or a high strength part, so that it can withstand the mechanical stress. So but in many cases, if it is not possible to generate an alternating filling pattern, means that in both the directions we must fill the material. But if it is not possible to generate an alternating filling pattern, what should we do? So in that case, each layer should be generated with a pattern parallel to the direction of the mechanical load. So suppose we have a part like this and it has to be loaded in this direction and fixed in this direction. We must deposit our material in such a way that each layer should be generated with pattern parallel to the direction of the mechanical load. So we can have a pattern which is parallel to the direction of the applied load. So two things by now we have been able to understand: how much dense our product must be or the prototype must be, and what must be the filling pattern of this volume, so that we are able to generate a prototype which can withstand the mechanical stress that is going to be exerted on the prototype for testing purposes. Now there can be chances of distortion, shrinkage and warping, because here the shrinkage will take place on solidification. So how to overcome that? Small layer thicknesses should be employed. So as we have already taken an example, again I am making the same part. So this thickness X must be less. So small layer thicknesses should be employed. High laser power, maybe greater than 36 watt for polymers, low scanning speed 3000 millimeter per second for polymers, and low temperature in the bed construction, that is approximately equal to 170 degree centigrade for polymers, are recommended. Very good guideline for the polymers, specifically for polymers making the prototypes out of the plastics. The laser power is given, the scanning speed is given, the bed temperature is also given, or the lower temperature in the bed. So all these parameters if we keep in mind while we are doing the rapid prototyping process, we will be able to make good prototypes which will not be prone to failure. Avoid designing elongated pieces. Parts with small values of length width ratio should be considered. So long parts are usually not recommended to be made by rapid prototyping. So we must take into account this length to width ratio while we are designing parts which have to be made by the rapid prototyping processes. The total surface area of the overhangs must be minimized, because whenever there will be a overhang, we need to provide the support structure, and already in one of the guidelines we have mentioned that we must try to reduce the use of support structure. So because support structures later on during the post processing have to be removed, and during the removal may lead to failure or damage to the other similar or small cross sectional parts. So therefore support structures we must try to minimize, and therefore this is coming from there only, that when support structures have to be minimized, the overhangs must also be minimized during the designing stage only. Now what is the surface finish? Small layer thicknesses and surface angles close to 90 degree should be used to obtain low values of surface roughness and reduce the staircase effect. Now what is the staircase effect? Now suppose this is one layer, this is on the exaggerated scale only I am showing, this is another layer. Suppose this is the third layer that we are depositing. Now suppose this is our platen on which we are making, this is moving down. So this is one layer, second layer, third layer, this is the staircase effect that takes place, and maybe this is the angle theta which is mentioned here. So we must try to minimize, because this will depend upon the layer thickness. This staircase effect can easily be optimized based on the individual layer thickness that we select, and based on the surface angle theta, we can manipulate these two, we can optimize these two to minimize the staircase effect. So smaller layer thickness is close to 25 microns and surface angles close to 90 degree should be used to obtain low values of surface roughness and reduce the staircase effect. Sloped surfaces should be minimized. So if we have sloped surfaces, maybe that we are making maybe something like this. So these surfaces will definitely have a staircase type of effect. So we must, sloped surfaces should be minimized during our design process. Now stability. Part should be oriented with its highest surface area on the building platform. This is to ensure the stability during construction, already discussed. I have explained it with the help of a diagram. Total curing of the part should be ensured in the curing process, very important, because the parts will polymerize and solidify once the curing is complete. So we must ensure complete curing of our prototyped parts. Pieces made of paper, wood or cornstarch should be coated to provide protection against the moisture. So maybe in some of the parts which we are making out of paper or wood or cornstarch as the raw material, as I have already told that rapid prototyping processes can be classified based upon the raw material that we are using. So if the material is made, if our prototype is made of paper, wood or cornstarch, we must try to coat it during our post processing of the prototype in order to avoid the moisture absorption. Support structure should be removed in small sections to prevent the damage of the model. So if we have used a support structure, we must remove it, so maybe chunk by chunk or in smaller sections, in order to avoid the damage that may happen to the overall prototype or the build material of the prototype. So with this we can conclude the today's session on rapid prototyping. So we have seen that once we are trying to make a prototype using any of the rapid prototyping processes, we must take into account these guidelines related to how much dense our prototype must be, what must be the orientation of the prototype. If the holes have to be made, what must be the orientation of the holes. The bigger portion of the prototype must be placed on the platen so that we can build it in a proper manner. So all these guidelines we must take into account related to the thickness of the individual layer, related to the surface angle. So if we follow all these guidelines, we will be easily able to produce a prototype which can be a fully functional prototype, or can be just a visual model of our object that we want to produce. So rapid prototyping is one of the important strategies that must be adopted during our product design process in order to save time. So we have seen that important parameters like the fill density, the deposition angles or the deposition directions of the material are definitely going to define the quality of the prototype that we are producing, and these must be taken care of and must be selected judiciously in order to make a good prototype. So maybe in our last session we will try to sum up the discussion that we have done over the last few weeks and try to see that how these guidelines are going to be useful for the product designers when they are going to design their products. Thank you.